Imagine a moment where everything you thought you knew about the universe is turned upside down. The James Webb Space Telescope, humanity's most powerful scientific tool, has just unveiled a discovery so shocking it's rewriting the rules of cosmic understanding. 7 massive galaxies, defying all expectations, emerged mere millions of years after the Big Bang. How did they form so quickly? What secrets are they hiding? These revelations challenge the very foundation of how we believe galaxies, stars, and the universe itself came to be. In this video, we'll take you on a journey back in time to the dawn of the cosmos, where wonders beyond imagination await. Part 1, The Astonishing Discovery, 7 Colossal Galaxies. Prepare to have your understanding of the cosmos completely redefined. Using the unparalleled power of the James Webb Space Telescope, astronomers have uncovered 7 massive galaxies that existed a mere 550 to 750 million years after the Big Bang. These galaxies, far from the small and simple systems scientists expected from such an early epoch, are extraordinary in their size and complexity. They are over 60 times larger than theoretical models predicted. A discovery so surprising that it has shaken the very foundations of galactic formation theory. To appreciate the significance of this, consider that the Big Bang occurred approximately 13.8 billion years ago. 400 millions of years afterward, the universe was a swirling, chaotic expanse of particles and energy, only beginning to settle into the building blocks of stars and galaxies. It was thought that the first galaxies to emerge would be modest in scale, dominated by young, bright blue stars that burn hot but quickly exhaust their fuel. Yet, what Webb has revealed are galaxies that defy these expectations entirely. Instead of immature, star-forming systems, these galaxies are home to ancient, red stars, indicators of a surprising level of maturity. The presence of these red stars is crucial. Red stars are older and cooler than their blue counterparts, suggesting that these galaxies must have begun forming stars almost immediately after the Big Bang. This leaves scientists grappling with the question, how did these systems manage to grow so quickly? Under traditional models, galaxies require billions of years to reach such a state, accreting gas and dust over time to form stars and expand. But here we have evidence of galaxies that achieved this in a fraction of that time. A feat that defies our understanding of the physics governing early cosmic evolution. Adding to the mystery is their scale. These galaxies are not merely larger than expected, they rival and even surpass the size of the Milky Way, which itself is the product of over 13 billion years of cosmic evolution. To encounter such immense and developed systems so early in the universe's timeline is like finding a fully grown tree in the middle of a sapling field. How did they accumulate such mass and complexity? What processes could have propelled their formation at such a breakneck pace? One intriguing possibility is that these galaxies are not isolated entities but rather part of something much larger, protoclusters. Protoclusters are the precursors to modern galaxy clusters. Vast networks of galaxies bound together by gravity, forming some of the largest structures in the universe. Within these dense cosmic environments, galaxies interact and merge, catalyzing bursts of star formation and accelerating their growth. This could explain why these galaxies appear so enormous and mature despite existing at such an early stage in cosmic history. It's as if these protoclusters served as galactic nurseries, where the conditions for rapid formation and evolution were exceptionally favorable. However, this hypothesis raises more questions than it answers. If these galaxies are indeed part of protoclusters, how did such clusters come together so soon after the Big Bang? The formation of protoclusters requires a significant concentration of dark matter to create the gravitational wells necessary for pulling in gas and dust. This implies that dark matter may have played an even more critical role in the early universe than previously believed. Alternatively, we could be missing a crucial piece of the puzzle, some unknown mechanism or phenomenon that allowed these galaxies to grow at an unprecedented rate. The discovery of these galaxies also has profound implications for our understanding of the timeline of the universe. Their existence challenges long-held assumptions about the speed and efficiency of galaxy formation. If galaxies of this scale and maturity were already present within 750 million years of the Big Bang, then the processes driving the assembly of cosmic structures must be far more dynamic and complex than we ever imagined. While these galaxies offer answers to some questions, they open the door to countless others. How many more such systems are out there, hidden in the vast reaches of the universe? Could these galaxies be the key to understanding the mysterious interplay of forces that shaped the early cosmos? As we continue to analyze the data from the James Webb Space Telescope, one thing is certain: the universe is far more extraordinary and enigmatic than we ever dared to dream. Part 2: Time and Distance, a journey to the early universe. The James Webb Space Telescope has given us an unprecedented glimpse into the distant past, capturing light that has traveled for 13.5 billion years to reach us. These galaxies existed when the universe was only 6% of its current age, a mere 750 million years after the Big Bang. Observing such ancient light isn't just about looking far away, it's about peering into a time when the universe was still in its infancy, revealing a realm where stars and galaxies were just beginning to form. This extraordinary achievement is possible thanks to Webb's unmatched sensitivity and its ability to observe in the infrared spectrum. Unlike visible light, which becomes faint and undetectable as it stretches across vast distances, infrared light can penetrate the depths of space, carrying with it a record of events that occurred billions of years ago. This is something its predecessor, the Hubble Space Telescope, couldn't fully achieve. Hubble brought us closer to the cosmos, but Webb has essentially given us a time machine, allowing us to see farther and deeper than ever before. What makes this journey back in time even more fascinating is the phenomenon known as redshift. As the universe expands, the light emitted by distant galaxies is stretched, shifting it toward the red end of the spectrum. Think of it like the sound of a siren from a passing ambulance. The pitch lowers as the vehicle moves away. Similarly, the light from ancient galaxies becomes stretched as it travels through space, its wavelength lengthening into the infrared range. This redshift is like a cosmic fingerprint, telling us how far away, and how long ago, these galaxies existed. For the galaxies observed by Webb, their extreme redshift indicates not only their distance but also their place in the early history of the universe. Light from these galaxies started its journey when the universe was still a chaotic expanse of gas and dark matter, where the first stars were only beginning to ignite. Imagine a universe so young that it hadn't yet formed the elements we now take for granted: no heavy metals, no carbon, no oxygen. What Webb has captured are the first tentative steps of a cosmos learning how to build itself. But this isn't just about numbers or distances, it's about understanding the story of creation. Each photon of light that reaches Webb's detectors is a messenger from the past, carrying with it secrets of a time long before Earth, long before the Sunday, and long before the galaxies we see today had even taken shape. These photons are echoes of the Big Bang, like ripples on a pond after a stone is thrown. They are a testament to the incredible journey of light across time and space. Webb's ability to capture these faint, ancient signals is nothing short of revolutionary. By analyzing this light, scientists can reconstruct the conditions of the early universe with remarkable precision. It's like piecing together a giant jigsaw puzzle where each observation provides another fragment of the picture. For instance, the discovery of these distant galaxies has revealed that star formation in the early universe was much more prolific than previously believed. What we thought were dim, simple systems are turning out to be vibrant hubs of activity, teeming with stars and possibly even protoplanets. This new understanding forces us to rethink the timeline of cosmic evolution. How did such large, complex systems form in such a short amount of time? Were the conditions of the early universe more conducive to rapid growth than we imagined? And if Webb can see these galaxies, how many more might still be hiding just beyond its current reach? The implications of this discovery extend beyond just understanding these galaxies. It reshapes our view of the universe's early days, showing us a time of explosive creativity and dynamic change. It's a reminder that the cosmos is not a static place but a constantly evolving entity, full of surprises waiting to be uncovered. As Webb continues to probe the depths of space, we are reminded of just how small yet interconnected we are in this vast cosmic story. Each discovery brings us closer to answering the age-old questions: where did we come from? And how did it all begin? Part 3: Challenging the role of supermassive black holes. Supermassive black holes have long been regarded as the linchpins of galaxy formation. These enormous objects, millions or billions of times the mass of our Sun, are thought to anchor galaxies, influencing their structure and growth. Their gravitational pull draws in gas and dust, and their powerful energy outputs, through a process called feedback, regulate star formation. However, the James Webb Space Telescope's recent observations are casting doubt on this well-established narrative. The 7 massive galaxies discovered by Webb, which existed just 550 to 750 million years after the Big Bang, seem to defy the need for central black holes. These galaxies, with their vast size and mature stars, appear to have grown without the regulatory influence of black hole feedback. Traditionally, feedback from supermassive black holes helps control the pace of star formation by expelling or heating gas. Yet these galaxies show no clear evidence of such control, leaving scientists questioning how they grew so large, so quickly. One alternative explanation involves a concept that is still largely theoretical: supermassive stars. These stars, far more massive than any we see today, may have played a pivotal role in the early universe. Formed under extreme conditions, supermassive stars would burn intensely for a short time, releasing enormous energy and scattering heavy elements across their surroundings through violent supernova explosions. This material could have catalyzed rapid star formation within galaxies, allowing them to expand and mature at a rate far exceeding what is seen in modern times. The idea of supermassive stars is particularly compelling in the context of the unique conditions of the early universe. Just after the Big Bang, the cosmos was a dense and dynamic environment, filled with abundant primordial gas and intense radiation. These factors may have enabled the formation of supermassive stars, which in turn could explain how galaxies reached such immense scales in such a short time. Unlike black holes, which tend to regulate growth, supermassive stars might have driven it, creating galaxies that didn't rely on black holes to anchor their structure. If this theory holds, it suggests that galaxy formation in the early universe operated under very different rules than it does today. This raises fundamental questions: are black holes truly essential to galaxy formation? Or are they just one possible pathway? Could the early cosmos have fostered other mechanisms, now extinct, that allowed galaxies to flourish in ways we've never imagined? These questions challenge some of the most foundational ideas in astrophysics. Until now, black holes have been seen as indispensable to the growth of large galaxies, shaping their structure and moderating their development. But the discovery of these enormous, ancient galaxies forces us to consider the possibility of alternative pathways to galaxy formation, pathways driven by forces we're only beginning to explore. This discovery also underscores the dynamism of the early universe. The galaxies observed by Webb are evidence of a cosmos teeming with creative energy, operating under conditions that encouraged rapid growth and evolution. They remind us that the universe's infancy was not a slow, methodical process but a time of explosive development, where massive structures emerged at incredible speed. The implications extend far beyond these 7 galaxies. If supermassive stars were key to early galaxy formation, why don't we see evidence of them today? Did they disappear as the universe expanded and cooled? Or are there remnants hidden in ways we haven't yet detected? Moreover, if some galaxies grew without black holes, what does this mean for the countless others we have yet to observe? The answers to these questions could reshape our understanding of cosmic evolution. As the James Webb Space Telescope continues its mission, it will likely uncover even more examples of early galaxies that challenge current models. These discoveries highlight the importance of keeping an open mind in science. Even the most established theories must evolve in the face of new evidence. And the universe seems determined to show us just how much we still have to learn. Part 4: Challenging the Dark Matter Theory. For decades, dark matter has been at the heart of cosmology, forming the framework for understanding how galaxies and large-scale structures develop. This invisible substance, making up around 27% of the universe, creates the gravitational pull necessary for gas and dust to coalesce into stars and galaxies. Yet, observations from the James Webb Space Telescope challenge this well-established theory. The massive galaxies Webb observed, existing only 550 to 750 million years after the Big Bang, are far too large and mature for their age under the current dark matter model. Conventional theories suggest dark matter halos slowly gather ordinary matter, driving the gradual growth of galaxies over billions of years. However, these ancient galaxies seem to have bypassed that slow process, forming at unprecedented speeds. One possibility is that the early universe operated under unique conditions that dark matter alone cannot explain. Scientists are now exploring the idea of primordial matter, a hypothetical form of matter distinct from both dark matter and ordinary baryonic matter. This primordial matter may have had properties enabling it to interact more directly with its surroundings, accelerating galaxy formation in ways we've never observed. Unlike dark matter, which interacts only through gravity, primordial matter could have had additional interactions with radiation or other forces present in the universe's infancy. These interactions might have created the ideal conditions for galaxies to form rapidly, acting as a catalyst for early cosmic evolution. While still speculative, the concept of primordial matter opens exciting new possibilities for understanding the fast-paced growth of these colossal systems. Another factor that could explain the unexpected speed of galaxy formation is dark energy, traditionally associated with the universe's accelerated expansion. Dark energy might have played a more active role in shaping small-scale structures during the universe's early years, by redistributing matter or influencing gravitational dynamics. Dark energy may have helped create pockets of high-density regions, enabling galaxies to form faster than previously thought. This reimagining of dark energy's influence suggests it could be more than just a force driving cosmic expansion. Instead, it might have directly impacted the formation of galaxies in the chaotic environment of the early universe. Such a perspective fundamentally alters our understanding of dark energy's role in cosmic history. If primordial matter or dark energy contributed to galaxy formation, it would require revising the standard cosmological model, which heavily relies on dark matter to explain the universe's structure. Webb's findings suggest that the processes shaping the first galaxies were far more dynamic and complex than current theories allow. These discoveries remind us that even foundational ideas in science must evolve with new evidence. Dark matter, while crucial, may not tell the whole story. Webb's data indicates that additional forces or phenomena could have shaped the early universe, forces that operated uniquely during its first billion years. The implications are profound. If primordial matter existed, why don't we observe it today? Did it vanish? Or are its effects hidden in ways we've yet to uncover? Similarly, if dark energy influenced galaxy formation, does it still play a similar role in modern cosmic evolution? As the James Webb Space Telescope continues to explore the depths of space, we'll likely uncover more galaxies that challenge our assumptions. Each new observation pushes the boundaries of what we know, offering glimpses of a universe more extraordinary and complex than we ever imagined. Part 5: The Technology and Role of the James Webb Telescope. The James Webb Space Telescope, JWST, represents the pinnacle of human ingenuity, designed to answer some of the universe's most profound questions. Unlike its predecessor, the Hubble Space Telescope, which primarily observed invisible and ultraviolet light, Webb specializes in capturing infrared light. This unique capability allows it to peer through clouds of cosmic dust and detect objects billions of light-years away, offering an unprecedented view of the early universe. Webb's advanced sensors and mirror technology are so powerful that they can capture faint light emitted by galaxies that formed just a few 100 million years after the Big Bang. One of Webb's groundbreaking achievements is its ability to reveal details about these ancient galaxies that were previously invisible to us. Its infrared capabilities enable it to detect light that has been stretched into longer wavelengths over billions of years due to the universe's expansion. This allows scientists to reconstruct the story of the cosmos in exquisite detail, from its chaotic beginnings to the formation of the first stars and galaxies. But Webb's mission extends far beyond studying the early universe. One of its most exciting applications lies in the search for extraterrestrial life. By analyzing the atmospheres of exoplanets, planets orbiting stars outside our solar system, Webb can detect chemical signatures that may indicate the presence of life. Molecules such as water vapor, methane, and oxygen, if found in the right combinations, could provide clues about whether these distant worlds are habitable. Webb's ability to study planets within our galaxy and even beyond offers a tantalizing possibility. We may be closer than ever to answering the age-old question of whether we are alone in the universe. Webb's contributions to the study of exoplanets are already remarkable. Early observations have detected atmospheres on several distant planets, revealing details about their compositions, temperatures, and potential for supporting life. This marks a significant leap in our understanding of planetary systems and their diversity. For instance, Webb has begun investigating planets located in the habitable zones of their stars, regions where temperatures may allow liquid water to exist. The prospect of identifying life-supporting planets, or even evidence of life itself, is no longer confined to the realm of science fiction. In addition to its role as a cosmic explorer, Webb is also paving the way for future astronomical endeavors. Upcoming projects, such as the Extremely Large Telescope (ELT) and the European Space Agency's Euclid mission, will build on Webb's findings, offering complementary insights into the universe's mysteries. The ELT, with its massive 39-meter mirror, will focus on observing planets and stars in unprecedented detail, while Euclid will study dark matter and dark energy, two of the most enigmatic forces shaping the cosmos. Together, these instruments represent a new era of collaborative astronomy, combining the strengths of space-based and ground-based observatories. Beyond its direct contributions to science, the technology developed for Webb has far-reaching implications across other fields. For instance, its advanced imaging systems and data processing techniques are already being adapted for use in medicine, such as improving diagnostic imaging. The precision engineering required for Webb's mirrors and sensors has applications in telecommunications, enhancing signal clarity and bandwidth. Additionally, Webb's thermal control systems, which maintain stable temperatures in the extreme conditions of space, are inspiring innovations in environmental monitoring and energy efficiency on Earth. These cross-disciplinary applications highlight the interconnected nature of scientific discovery. The tools and techniques created for space exploration often lead to breakthroughs in entirely unrelated fields, improving our lives in ways we never anticipated. Webb's legacy, therefore, is not just about uncovering the secrets of the universe, it's also about driving innovation and inspiring future generations of scientists and engineers. As Webb continues to push the boundaries of what we can observe, it serves as a reminder of humanity's relentless curiosity and capacity for collaboration. Its ability to look back in time and explore the unknown offers a profound sense of connection to the cosmos. From investigating the earliest galaxies to probing the atmospheres of distant planets, Webb is not just a telescope, it's a bridge between the mysteries of the universe and our understanding of ourselves. Part 6, The Journey Ahead, Unanswered Questions. The discoveries made by the James Webb Space Telescope have raised more questions than they've answered, leaving scientists with a plethora of mysteries to unravel. Among the most intriguing avenues for future research is the role of cosmic flow, the streams of gas and dark matter coursing through the vast filaments of the universe. These flows are thought to act as highways, channeling material into regions of high density where galaxies form. Understanding how these cosmic rivers influence the growth of the colossal galaxies observed by Webb could shed light on why these systems formed so quickly and at such a massive scale. Dark energy, which accounts for nearly 70% of the universe, is another focus of investigation. Known primarily for driving the universe's accelerating expansion, some scientists now propose that dark energy may have influenced small-scale structures in the early cosmos. It's possible that its subtle yet omnipresent force helped create conditions that allowed galaxies to grow at an unprecedented pace. If this theory holds, it could fundamentally reshape our understanding of dark energy's role, not just as a large-scale force but as an active participant in cosmic evolution. Adding to the complexity is the tantalizing hypothesis of the multiverse. Could these massive galaxies be evidence of gravitational interactions with a neighboring universe? Some researchers speculate that if multiple universes exist, their overlapping gravitational fields could have influenced the formation of structures in our own cosmos. While this idea is speculative, it invites us to consider whether the boundaries of our universe are truly as definitive as we've assumed. Beyond the scientific, these discoveries pose profound philosophical questions. The existence of such galaxies, defying our current understanding, challenges us to rethink the narrative of the universe's origins. Were these systems formed by processes unique to the early cosmos? Or do they point to something more fundamental about the laws of physics? More broadly, what does their existence reveal about the purpose and trajectory of the universe? These questions remind us that science and philosophy often intertwine, with discoveries in one field inspiring deeper reflection in the other. As we delve deeper into these mysteries, the significance of Webb's mission becomes ever clearer. This telescope is not just a tool for observation, it's a time machine, a bridge between the distant past and our present, and a reminder of the extraordinary complexity of the universe. With every image it captures, Webb expands the scope of what we know and challenges us to confront the vastness of what we do not. The implications of these findings extend far beyond academia. They invite us, as individuals, to reflect on our place in the cosmos. If galaxies of this scale could emerge so early in the universe's history, what does that say about the forces that shaped not only the cosmos but also our existence within it? Are we simply observers in this grand story? Or does our curiosity and drive to explore hint at a deeper connection to the universe's purpose? Webb's discoveries are not just about rewriting textbooks, they are about redefining the boundaries of human knowledge. They inspire us to think beyond the limits of our current understanding, to embrace the unknown, and to push forward in the quest for answers. As we continue to explore, the lessons we learn will not only deepen our grasp of the cosmos but also remind us of the boundless potential of human curiosity and ingenuity. The discoveries made by the James Webb Space Telescope are just the beginning of a thrilling journey into the mysteries of the cosmos. If you enjoyed exploring these incredible insights, don't forget to like, share, and subscribe to our channel for more captivating content about the universe. Thank you for watching. And stay tuned as we continue uncovering the secrets of space together.